After I'm gone, your Earth will be free to live out its miserable span of existence as one of my satellites. And that's how it's going to be.
Time is running out. Any of it, walking, 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 any of it, any of it, any of it, walking, highest reach over the sky, any of it, walking, highest reach over the sky, any of it, walking, highest reach over the sky.
After I'm
clear reach of Earth City.
Okay, so welcome back everybody. So last night I uploaded Monday's lecture, which is more examples of 14.1 stuff. So the most important thing from that lecture is the example of swapping the order of integration for simple regions. So we had already done a couple of examples of that when we first defined the double integral, but the examples that we did were kind of easy or obvious examples. So I did an example in the previous lecture of one that's a little less obvious, where it's actually undoable one way. So you actually can't do the double integral in the way that it's written, and so you have to swap the order of integration in order to actually be able to do that double integral. So that's something that can happen, so you should definitely have a look at that. One of the other things I talked about in the last lecture is the use of symmetry. And so the use of symmetry can make some of these computations that you're doing with double integrals a lot easier. If you notice that the thing that you're integrating and the region that you're integrating over are symmetric with respect to each other in some nice way that you can take advantage of. So that's the most important bit. So it's only a couple of examples I did, but those are important. So anyway, on to the next thing that I wanted to talk about, and kind of primarily the first motivating example here is what if I want to do a double integral of some function over a region that looks like this. I did a pretty bad job there, but this is supposed to be a region bounded between two circles, so this is an annulus. Right, is the Latin word for this shape. So the region bounded between two circles, this is an annular region or an annulus. If this is my region R, what's the problem with this? As we saw previously, this is not simple, or it's worse than that. It's not vertically, so it's not vertically simple, and it's not horizontally simple. Okay, and yet we're still going to integrate over it. Okay, so what's maybe kind of intuitive way that you might have to think about how you can integrate? If I tell you that it's possible to integrate over this, even though it's not vertically or horizontally simple, what might be kind of your basic guess as to how you're going to do this? So one way that we could do this is we could split this into regions in a nice enough way. So there's multiple ways I could do this, but right now I'm going to split it into two regions in this way. I'm going to split it into two regions like this. Okay, and I'm going to split it into these two regions, where my top region I will call R sub 1, and my bottom region I will call R sub 2. And I view R as a union of these two regions. Okay, and so R is viewed as being composed of these two regions, and the intersection of these two regions is a one-dimensional set. That one-dimensional set doesn't have area, right? The area of a one-dimensional set is 0, so that's it. Okay, what that means when I say that's it, I mean if we're talking about area or something contributing to area, we don't have to worry about it because it's a one-dimensional thing. And so viewing R as a union of R1 and R2, I can do the following. This is something that I haven't really mentioned before, but if I'm integrating some function over R, I could do this double integral as the double integral over the piece R1, and I could add to that the double integral of the exact same thing over the piece R2. Now, a couple of things here. One, like, where did I come up with this fact? This fact works for the same reason that you can break up a single integral in Calc 1 over an interval, right? But in lower dimensions, right, breaking up an interval, you're splitting it at a point, which is 0-dimensional, right? So you're splitting that interval up at a point, and of course you can sum, you can do that integral as a sum of integrals of the exact same function over all of the parts, so long as you're exhaustive, right? Exhaustive meaning I totally cover this region. Now, of course, there's nothing special about splitting this into two regions. I could split this into any number of regions. I could split this into fourths. I could split it into eighths. Any number of things I could split it into. As long as I'm exhaustively filling out that region, I can compute this. Now, what sucks about doing it this way? Well, I mean, it just adds more work. This now, instead of doing a single double integral, now I have to do 2 or 3 or 4 or however many, right? But what's the benefit of doing it this way? Note that the regions that I split it into are actually vertically simple. So R1 and R2 are both vertically simple. Okay. And so you can deal with a region like this by splitting it like that. Okay, but that's not going to be our focus. And the reason that's not going to be our focus is it turns out there's just a much better way of doing these things that isn't so nasty, and also simultaneously applies to some regions that are much worse than this. So how about this region? How about this region? Consider an Archimedean spiral starting here at the origin. Maybe this does something like and then consider a different Archimedean spiral. Maybe spirals out something like this. And consider the region R bounded between these two Archimedean spirals. Okay, so here's my region R. And say that I want to integrate over this region. Okay. So now, how would I do this if I was going to split it up? Right? Well, I would have to break it up into several pieces, and you can think to yourself how you might do that, right? So I could break it up as a left and right function on this piece. Right? In fact, I need to make sure that my function passes the horizontal line test if I'm using left and right functions. So this does. And then I could split this into another piece. And then I could split this into another piece. And then lastly, I have that piece. So I could break this into like 4 pieces and do it, but this would be horrible. This would take me forever to do it this way. And so we're going to go over a method that is going to allow us to deal with both of these really easily, okay, in one step. All right. The key thing to note here is that some regions look a lot simpler in other types of coordinates. Okay, so our default view is Cartesian, right, named after Descartes, so it's Cartesian or rectangular coordinates. So whenever you hear someone say Cartesian or rectangular coordinates, this is my normal coordinates for the plane xy. Okay, so our default view of the plane of R2 is Cartesian. It's the normal coordinates that you were introduced to forever ago, right? But it turns out that some regions are just much nicer or much simpler in other types of coordinates. So some regions are much simpler, and I put quotes there because I am definitely drawing a parallel here between this term and what we mean when we say simple. Because that's going to be the case for a lot of these things, that they are going to turn out to be actually simple regions. So for instance, this in the coordinates we're going to switch to is going to be a rectangle. Okay, so this is going to be a rectangle in our new coordinates. Okay, so some regions are much simpler in other types of coordinates. Okay, now at the very end of this chapter, or near the very end of this chapter, we'll talk about more general coordinate transformations. But for right now, we are going to focus on a single type, and that's polar coordinates. Okay, so the things that we focus on for polar coordinates are parts of circles. So circular things that are nicer or more nicely described in polar coordinates. Another example are these spirals. This is very easy to describe in polar coordinates. Describing this in rectangular or Cartesian coordinates is a mess. This would be a disaster. Describing this in Cartesian coordinates, but it's actually really easy to describe in polar coordinates. So some of you may remember how you would write this in polar coordinates. You can type it in the chat if you remember, but we'll do that here by the end of today. Okay, and so quick refresher of polar coordinates. What's the idea here? Okay, so our quick refresher is that if I have a point xy in my plane, I want to view this as the same as a point that I call r theta. So I'm still using 2 real parameters here. Okay, but my real parameters now are not x and y, they're r and theta. So of course x and y denote a very simple relationship, right? The first slot is however many units x I am to the left or right, and the second slot is the y coordinate, it's however many units I am up or down. All right. Okay, but where do I get r and theta from? Okay. Well, the idea here is that this point has a distance, right, to the origin. That distance is r. Okay. What is the thing that I'm doing with polar coordinates? I'm viewing this point as lying on a circle having angle theta measured from the positive x-axis and having radius r, which is just the distance from my point to the origin. Okay. Jack, x is equal to r cosine theta. Right, that's exactly right. And that is the statement that this is the x-coordinate of a point lying on a circle of radius r centered at the origin. Right. And this is the theta that we're measuring here. And so, just as Jack said in the chat, the relationships is that x is r cosine theta and that y is r sine theta. Okay. This is my transformation that takes me from polar coordinates to rectangular coordinates. Now, you might say, how do I know what direction I'm going in? So I can go in either direction. This is the direction from polar to rectangular coordinates. Why? Because if I have r and theta in front of me, then computing x and y is easy from this, right? I just plug r and theta into these two relations and I'm good to go. What is the relation going in the other direction, right? So x squared plus y squared is equal to r squared, or equivalently, if you like, you can write it in the other way, which is square root of x squared plus y squared is equal to r. That's the statement that this distance from this point to the origin is r, right? Or that the point xy lies on a circular radius r, centered at the origin. So this is the relationship between x, y, and r. Okay, and so if I have x and y, computing r is simple from this relation. Okay, and then how do I find theta? Well, notice that y over x is equal to r sine theta over r cosine theta. The r's cancel. Sine theta over cosine theta is tan theta. And so y over x is equal to tan theta, or theta is arctan of y over x. And so the two relationships that relate x and y to r and theta going the other direction are r is equal to square root of x squared plus y squared, and theta is arctan of y over x. Okay, so there's your brief review of polar coordinates. So I'm not going to go over switching between them, but if you're confused, that's something that you should review. Some basic examples of changing back and forth between rectangular and polar coordinates. Okay, and so what is nice about polar coordinates? So something that you did toward the end of Calc 2 is that you use polar coordinates to describe functions in terms of polar coordinates that were very nasty or nearly impossible to describe in terms of rectangular coordinates. So what kind of thing might that look like? Well, here's the idea. If I consider functions so I'm in the xy plane still, okay, and rather than thinking of a function y is a function of x, forget about that for a second. I want to think about writing functions in polar coordinates. So r is a function of theta, all right? And so what might this look like, where theta is between some angular values, alpha and beta? Now, you might recall here, if theta is equal to alpha, what does that look like in the xy plane? What does the equation theta equals alpha look like? Think about it. I'm thinking of all points r theta in the xy plane that satisfy this angular equation theta is equal to alpha. So any point that has angle alpha is going to lie on whatever this thing is. What is this thing? It's a line. It's just a line through the origin. So let me get this is no good. Let me get my straight edge. I can't draw straight. Where's my... Okay. Okay, let's draw straight figures now. That will be better than what I'm trying to do. Okay, there we go. Oh, and I went off look at that. Terrible. Okay, so this is alpha, right? That measurement. And so this line through the origin is the line theta equals alpha. The line theta equals beta might look something like this. And then what might a function r equals f of theta look like? It might be something that looks like this. Okay. Could be some weird thing like this. It could actually be even weirder than that. It could cross over and under itself a bunch, both with respect to x and y. Okay, so maybe this is r is equal to like f, say sub 2 of theta, and another function might look like this. Okay, so this is r is equal to f sub 1 of theta. And thus the region in between here is my region R. Okay. All right. So the idea is that if we could deal with regions like this in polar coordinates in general, this opens the door for a huge amount of examples that we can do, because this type of region is a really, really general thing. This includes all kinds of nasty things that would have been very, very hard to do in rectangular coordinates. Now in Calc 2, when you had a region like this, you were interested in just finding its area, right? That was kind of the big application of polar coordinate stuff that you did at the very end of that section. But for us, we want to compute the integral, right? The double integral of a function on a region that looks like this. Okay, so that's the idea. Just to give you an example of how these polar functions can look, so I noticed no one put it in chat, but what does the graph of r is equal to theta look like? So you have one last chance here to guess what this looks like. Okay, no one said it. So r is equal to theta looks like this. All right, and like r is equal to 2 theta looks like this. Okay, and so that region that we described earlier is actually really, really simple in polar coordinates, right? No crazy functions are required here. Okay, all right. So let's say that I have a region R, and that region can be written in polar coordinates like this. So I have a region R, might look something like this. It is a region in polar coordinates that is between the graph of two polar functions. So R, right, this is the polar coordinate R, is bounded above and below in polar coordinates by functions of theta. There is an additional thing here. I'm actually assuming that this is greater than or equal to 0. The technicality there, I won't do an example of how it affects. Actually, do I want to go ahead and do an example of this? Probably, yeah. I'll go ahead and do an example. So there's a technicality here. We actually want to set this up so that both of these are greater than or equal to 0. Because if they're not, there's something stupid that can happen that I'll show you later. So maybe I should say that both of these are greater than or equal to 0. So let me get rid of R here for a second. I'll say that both of these are greater than or equal to 0. So my region R is described as being the region bounded between the graph of two polar functions. Both these polar functions are greater than or equal to 0. And theta itself is bounded between two angular values, alpha and beta. Okay. All right, and so here's my region R. That might be something that it looks like here. Here's my setup. Okay. So this allows me to compute the double integral over R of some function dA using polar coordinates. Now, this thing that I'm about to write on the next page might look a little bit confusing at first, and you might say, like, where does this come from? And I'm going to put off those questions until the end of this chapter, because we will prove, or, well, I'm not going to prove it, but I will state a theorem that this is a special case of. Okay. So this allows us to compute this double integral over a region like this using polar coordinates. How can I do that? Here's how. So double integrals in polar coordinates. So how does this work? So suppose that h1 and h2 are two functions that are continuous on an interval alpha, beta, where alpha and beta, or rather the difference of beta minus alpha, that's greater than or equal to 0 and less than or equal to 2 pi. Okay, remember these are angular values, so we can always set this up. We don't have to worry about that. And that both of these are non-negative functions of theta, with h sub 2 dominating h sub 1. Okay, for all alpha less than or equal to theta, less than or equal to beta. So for all beta or theta between alpha and beta. Okay, so let R be the region that we wrote before as it's the region between the polar graphs. So this is little r is bounded above by h sub 2 of theta and below by h sub 1 of theta. Now, I've already included this assumption that both of these are non-negative here, so I'm not going to write it again to give myself more room. And theta is between alpha and beta. So written out in words, this is the region between the polar graphs r equals h sub 1 theta and r equals h sub 2 theta for theta between alpha and beta. So this is a long-winded way of saying it. What I've boxed is the shortcut way of saying it. Okay. All right, then if f is continuous on R, then the double integral over that region R of f of xy dA can be computed as the integral from alpha to beta, the integral from h sub 1 of theta to h sub 2 of theta of f. Now I'm tempted to write parentheses and then write x and y here. Why do I know that that's going to be wrong? Like, what intuitively is going on here to let me know that I'm not going to write this as an integral of f of xy? Because x and y are Cartesian coordinates, or rectangular coordinates. And that is not going to make sense for us in polar coordinates. We want everything on the right-hand side to be in terms of polar coordinates. So everything here is going to be in terms of polar coordinates. So instead of writing f of xy here, what am I going to write? I'm putting it in terms of polar coordinates. So I'm going to do this substitution. X is r cosine theta, y is r sine theta. So instead of writing f of xy, this is f of x cosine theta, or sorry, not x cosine theta, r cosine theta, and r sine theta. Those are the things that get plugged in the slots. Okay, now comes something else. This is extra. Okay, times r dr d theta. So I'm doing the integral with respect to r first, then I'm doing the integral with respect to theta. This is always like this. I'm not really going to change the order of integration here. This is the way of doing it. So, big thing to note, right? After you've seen the form that takes, big thing to note here, right? And yes, so I see in chat now, do we have to specify a region like this in our work, or is it considered a given? Kaylee, it depends on the question. Sometimes you're going to be given a region that basically is already, everything is given to you in polar coordinates. Other times, I'm just going to give you a region, and I'm going to say find this double integral. And if it takes you 4 hours to do it because you didn't see to plug it into, you didn't see to use polar coordinates, well, that's that's on you, right? So that's the warning. The warning is that many times I'm not going to tell you anything about what type of coordinates to use. It's going to be totally up to you. But the good news is that if you think about what you're doing before you set about doing it, there are hints that you should see the way that the problem is stated that automatically tell you should be using polar coordinates. So for polar coordinates, it's a pretty simple computation. You just look at the thing that you're integrating and the region that you're integrating over, and you say, is this a part of a circle, or is it a region that is simpler in polar coordinates? And if the answer is yes, then you should be using polar coordinates. If the answer is no, then you should be using rectangular coordinates. And that's how it goes. So this is not the only coordinate change that we're going to do. We're going to do multiple different specific coordinate changes like this. This is just the first example. Okay, and so you're going to have a whole list of ways that you can compute multiple integrals. And in general, I'm not going to tell you how to do it. I'm just going to say do it. And you have to figure out what you should use. Jacob, limits and integrals in terms of r and theta. That's right. And I see Jack gave me the things to plug into F here. Okay. So anyway, what's the big thing to note here? There's this extra factor of r. You cannot forget this. If you forget it, everything you do after this is wrong. You're going to get the wrong answer. So you have to remember this. This factor always shows up when you're doing a polar coordinates integral. You might say, where does this come from? And that's a good question. But again, I'm going to defer until the end of the chapter because then you will see exactly where it comes from. Okay. So for us right now, it comes from out of the void. Okay. From absolutely nothing. But we'll see exactly where it comes from later. Okay. So we just defined this thing. It's a great time to do an example of one of these. So let's consider the following example. This is actually like a multi-example. This is straight out of the textbook. This is example 1 from this section, but it's a good one because I'm going to do this over 3 regions basically all at once. So first example that I want to do here. Let R be the region bounded between circles of radius 1 and 2 centered at the origin. Okay. Compute the double integral over R of 3x plus 8y squared dA. Okay. So if we draw R is that annular region that motivated us to talk about polar coordinates in the first place, right? So here's 1, here's 2. So here's my, oh, that is the worst circle I think I've ever drawn in my life. That's probably the second worst. All right, so here's what R looks like. Okay. If we were in topology, we'd be in good shape. Because in topology, this is pretty much identical topologically to a perfectly drawn one, all right? But anyway, so here's my annular region. It's the region bounded between circles radius 1 and 2. I'm just asked to compute this, all right? Now, this is a perfect example of type of problem that you might see with this. Notice I didn't tell you to do this in polar coordinates, but you look at this and you say, well, it's stupid to do this using anything other than polar coordinates because it's going to be a lot more work, right? First of all, I can't even do it the way it is. I would have to split it up into multiple regions or something, right? And I don't want to do that. So in polar coordinates, how would I describe R? In rectangular coordinates, it's actually, just describing this in rectangular coordinates is kind of horrible, right? Because there's not a real good way of writing what it means in terms of X and Y to be bounded between circles of radius 1 and 2. But in polar coordinates, it's really, really simple. So in polar coordinates, how do I write this? Right, so this is in my XY plane. But in polar coordinates, this region is the region R that is bounded, my radius, little r, is bounded between what and what? Well, I'm told right here, it's bounded between 1 and 2. And theta is bounded between what and what? Remember, theta is my angular value measured from the positive x-axis. So here it is. Theta is, I need to spin this around. All right, if I want to get the entire ring, theta would need to go from 0, the positive x-axis, all the way back. That's 2 pi worth of angles, right? All right, notice here's a great place, and we'll talk about this here in a second. What would I do if this region wasn't the region as I've listed it here, but was actually the half ring instead? How would I alter my description here in polar coordinates? Well, instead of r being between 1 and 2 and theta being between 0 and 2 pi, r would still be between 1 and 2, but theta would be between 0 and pi if I wanted the upper ring. It would be between pi and 2 pi if I wanted the lower part of the ring, right? If I wanted this first quarter of the ring, theta would be between 0 and pi over 2. If I wanted the third quarter, theta would be between pi and 3 pi over 2, for instance. Okay? But notice, this is as easy as it gets in polar coordinates. What do I mean? If I were to draw this picture in the r theta plane, what does this look like? Well, here's 1, here's 2. Theta goes from 0 to 2 pi. And so this is a rectangle. Now, this isn't really the same region R. We'll call this region S. Okay? But somehow, some way, these regions are related by the transformation that takes polar coordinates to rectangular coordinates or rectangular coordinates to polar coordinates. So if you want to view what this transformation of these coordinates is doing, if you're going from rectangular coordinates to polar coordinates, it is like breaking this and then whoop, like undoing it, right? So imagine this made out of some kind of stretchy material. It's like you're cutting here and then unwrapping it, and what you're left with is this strip. Okay, going in reverse, of course, you're taking this strip and stretching it out and then whoop, doing this kind of, you're turning it in a circle and then gluing it back to the other end, right? The reason, your textbook doesn't go over this at this stage, but the reason I'm going over this now is because this will be handy when we do this at the end of the chapter, okay, to see what it is that's actually going on here. Okay, so I want to compute this. All right, so how do I go about doing it? Let's remember my thing. This was my statement that if everything is satisfied, and here it obviously is, it's a very simple case, then this double integral can be computed in this very specific way. Okay, and so I want to write this is then equal to the integral from 0 to 2 pi. Right, the theta integral is always on the outside. The integral from 1 to 2 of 3x plus 8y squared, but I'm plugging in my polar coordinate transformation, right? So this is 3 times r cosine theta plus 8 times r sine theta all squared now what? Times r, which is our extra special factor here that always shows up. Dr d theta. Okay. Now what? Well, let's multiply everything here by r and do this expansion, make this look a little nicer. So this is the integral from 0 to 2 pi, the integral from 1 to 2 of, so this is going to be 3r squared cosine theta plus 8, this is r squared times r is r cubed, so this is 8r cubed sine squared theta dr d theta. Okay. So now I want to do this first integral with respect to r, right? So I can ignore the trig functions for now. So I have the integral from 0 to 2 pi. I want to compute this integral here. So this is, with respect to r, 3r squared cosine theta. I treat cosine theta just like a constant. What's the integral of 3r squared cosine theta? This is, well, this would be 3 times r cubed over 3. So this is r cubed cosine theta, right, is what I get from integrating the first term. Second term, I have 8r cubed. That is going to become plus 2r to the fourth sine squared theta. And that, of course, is evaluated from 1 to 2 d theta. Okay. So let's quickly see how this works out. So evaluating this from 1 to 2, let's think here. I can actually evaluate these separately. So here I plug in 2 cubed minus 1 cubed, so 8 minus 1, that's 7. So this is the integral from 0 to 2 pi of 7 cosine theta. I have 2 r to the fourth here, so that's 2 times r to the fourth is, 2 to the fourth is 16, minus 1 to the fourth is 15, so that's 2 times 15, or 30. Right, so this is plus 30 sine squared theta d theta. And now I'm ready to do my integral with respect to theta. Now comes a great time for the following aside. So let's box this. We still have work to do, but let's box this for now. And let's do an aside, which is something that you might have some questions about since I first started talking about integrals in this class. So here's an aside. I have very often talked about how the integrals in this class are easier than the integrals in Calc 2. But you probably have specific questions about exactly how much easier they are. Kind of the best way to phrase that maybe is the question, what sorts of integral tricks are needed? In this course. Okay. So, here's the answer. I'll try to be exhaustive and try not to forget anything. So general list of basic integrals. When I say general list of basic integrals, these are the integration tables you might find in the front or back of a calculus textbook of your choice. So these are integration tables. So I'm not saying that you should have memorized necessarily how to integrate some more exotic functions, but of course polynomials, you should know how to do polynomials, you should know how to do exponential functions, you should know how to compute the integral of natural log of x. So if you've forgotten how to do that, you should do that, because that's a good one. Typically, in like a normal Calc 1 class, I maybe wouldn't do an integration by parts problem. I think you should know integration by parts just because it's awesome, but you don't need to use it for this. You're not going to need to use integration by parts. You are going to need to know the basic integrals. So the trig integrals, exponential polynomials. That's what we mean by a simple integration table. What else do you need to know? Substitution. So using that list together with substitution, and when I say substitution, I'm not including trig sub. You don't need to remember trig sub. Just plain old U sub. Okay, so plain old U substitution is something that you need to be familiar with. So this list of basic integrals contains, like the power rule for polynomial things. You need to know the Pythagorean identity. So you need to know sine squared theta plus cosine squared theta is equal to 1. Of course, you can derive the other Pythagorean identities from this by dividing both sides by sine squared or cosine squared. So this is really the important one. The thing that is maybe a little non-standard that you should know is power reduction formulas for trig function. Power reduction formulas. For trig functions. What are those? Well, the basic ones are ones for sine squared and cosine squared. Now, how do I remember what it is that goes on here? So, when I'm reducing sine squared and cosine squared, here's how I remember them after all these years. Both of them have the exact same form. It's 1 and then something, and then cosine of 2 theta over 2. So both of them have this form. The question is, can you remember which one has the plus and which one has the minus? There's a very easy way of doing this. Consider what the value is when theta is equal to 0, right? So when theta is equal to 0, I would have sine squared of 0. That needs to be 0, right? Because that's just 0 squared. And so this quantity needs to be 0. But when I plug in 0 here, I get cosine of 0, which is 1. So I get 1 blank 1 over 2. I need that to be 0, so what does that need to be? That needs to be a minus. Similarly, cosine of 0 is 1, so cosine squared 0 is 1 squared, so it's just 1. So this needs to be a 1. I would have 1 blank 1 over 2. Well, that's only 1 when that's a plus. So that's an easy way to remember these formulas. This is how you can deal with some trig integrals that are going to result from what it is you're doing in these problems. There's some other just general, integration trickery stuff that you can do to make your life easier. So for instance, doing these evaluations, when you have an odd function, like an odd polynomial, right? So a polynomial that only has the odd terms. Then when you evaluate, say, on like a symmetric interval, then, well, that's just the same as plugging in one of the endpoints and doubling it, right? So plug in the top endpoint and double it. It's an easy way to save a bunch of time. Okay. So So this is kind of what you're going to need to use for this class typically. If you need to use anything harder, then I'll give you a hint for that problem. Okay, so let's return to our boxed thing here. There it is. Okay, so let's continue on. Okay, so continuing on here. This is equal to, now I'm going to actually do this integral. So before I do this integral, the reason I wanted to do that aside is I have a sine squared theta here. That has no easy integral. I need to use power reduction formulas to make that something that I can do a lot more easily. So this is the integral from 0 to 2 pi of 7 cosine theta. That's perfectly easy to integrate. Plus 30 times, I'm going to use power reduction formula for sine. So this is 30 times 1 minus cosine of 2 theta over 2 d theta. All right, and so now multiplying this by 1/2 and then distributing, I would have the integral from 0 to 2 pi of 7 cosine theta plus 15 minus 15 times cosine of 2 theta d theta. And now I have something that I can easily integrate. All right, so how does this work? So integrating this, what's the integral of cosine of theta? Well, that's just sine theta, so pulling the 7 out, this is 7 sine theta. This term, 15 d theta, the integral of that is 15 theta, of course. Okay, and then lastly, I have I have cosine of 2 theta here, right? So remember, I have to use u sub. If u is equal to 2 theta, then I'm going to get an extra factor of 2, which I have to account for by multiplying by 1/2 on the outside of the integral. So this becomes 15 over 2 times sine of 2 theta. And all this is evaluated from 0 to 2 pi. Okay. Okay, so when I do that, what do I get? Well, what do I notice first of all? Again, almost all these problems have this. There's almost always at least one way you can shorten the amount of work you have to do. Okay, so I look at this and I just notice, well, sine of theta and sine of 2 theta are both 0 at both endpoints. So I plug in 2 pi into both of these, I get 0. Plug in 0 to both of these, I get 0. So those terms go away, and the only term that contributes to anything to this evaluation is the middle term, 15 theta. And so this is just 15 times 2 pi minus 0, so 30 pi. Okay. All right. Questions about that? I don't see any in the chat. Okay. Now, there's a couple of questions I could ask here. This is a nice way to reinforce ideas of symmetry here. Notice that if I go back to my original picture, I have an expression here, 3x plus 8y squared. Is this symmetric with respect to this region that I have? Well, not entirely, right? Not completely. How so? Well, it matters whether or not x is to the left or to the right, right? There's a difference in this integrand whether x is positive or negative. But there is not a difference between whether y is positive or negative. And so this expression and this double integral has symmetry with respect to the top versus bottom, meaning that the volume of, given by this thing, or computing this double integral here, is going to be the same if I compute it on the whole ring versus computing it on the top or the bottom and doubling it. Okay, and you can check that directly. If you change this r, if you go from 0 to pi instead of 0 to 2 pi, what you would get at this last step is you get 15 times pi. So you get exactly half that. Okay, but notice that is, you can't use this symmetry universally because it's not symmetric in every possible way, again, because of this x here. There only being a single power of x here. So I talk about that a little bit in the last lecture, if you haven't seen it yet, so I do more examples of that. So that's one single example of using polar coordinates. I'll do at least one more on Friday's lecture, and then we'll move on to triple integrals. Okay. So this is how this works. For tomorrow's discussion, you'll do more examples of double integrals, either using polar coordinates or not. So so it will be fair game. Any question about double integrals, you'll be asked to work through. Okay. Anyway, so that's that. I'll see you all in lecture on Friday.